Welcome back to Differential Equations. In this lecture, we're going to introduce and learn how to solve a type of differential equation called an exact equation. This topic tends to be rather difficult for students. We're going to draw on some topics from multivariable calculus, Calc 3. If you completed Calc 3 already with partial derivatives, great. If you haven't taken Calc 3 yet, or are not familiar with partial derivatives, don't worry, we're going to go through and introduce them in this lecture. All right, so as always, to get started, let's consider an example here. So let's think back to our previous topics. We can solve first order ODEs that are separable, and most recently, we can solve ones that are called homogeneous. Now let's see if this one is solvable with either of those techniques or methods. Let's try to separate it by multiplying the dx over. And notice immediately, due to the terms inside the parentheses containing x and y, on the right-hand side, we're not going to be able to separate this. All right, also notice inside the parentheses on the right-hand side, we have negative 2x, which is a degree 1 term, and then also inside the parentheses, we have negative y squared, which is a degree 2 term. Recall, homogeneous equations have terms all of the same degree. And since here we have a degree 1 term with a degree 2 term, this ODE is not homogeneous. So we're kind of stuck because it's not separable, it's not homogeneous. We're going to need a new method to solve this ODE. Now, how we're going to solve this is we're going to kind of go into another branch of mathematics, multivariable calculus, and look at the ODE from that perspective. We'll use the tools of multivariable calculus, partial derivatives, to bring them back to solve our differential equation. We'll get to that all through the intro here. All right, so to lead us to our starting place, let's continue rewriting our differential equation. Starting with the right-hand side, notice inside the parentheses, I can factor a negative out. And then the entire right-hand side, the entire dx term, I can add that to the left side. So we get this differential equation, which we're going to call differential form. We'll define this a little bit later within this lecture. All right, and the key here that we're going to rely on, if you, again, you have completed Calc 3, is we're going to look at the ODE in differential form as looking very close to what was called in Calc 3 a total differential. All right, now, for those of you that haven't completed Calc 3, in a minute or so, we're going to introduce differentials from basically a Calc 2 perspective to give you some idea of what differentials are and how they relate to this ODE. All right, so just a quick background if you've completed multivariable calculus. If we have a function of two variables, the total differential involves partial derivatives. Partial derivative with respect to x and the partial derivative with respect to y. That's the topic we're going to use. Partial derivatives, we're going to review that as we're going to need it for our course a little bit later in this lecture. All right, so let's not get to partial derivatives yet. Let's just kind of go into detail about what differentials are for our purposes in differential equations. So let's think back to Calc 2 when you probably used substitution or U substitution to evaluate integrals. So think back, you would choose a U equals some function of x, and with your choice of U, you would calculate the differential du, which if u is f of x, the differential du equals f prime of x times dx. back then in Calc 2, you can basically say derivatives and differentials are the same thing. All right, now when you get to Calc 3, or if you've completed Calc 3, you transition from functions of one variable to functions of two or more variables. So let's consider here, very similar to U substitution, let's suppose we have a function of two variables, a function f of x and y. Now, I don't want to go into full detail about what differentials are, but at a basic level, they represent a total amount of change in a function value. All right, the difference is previous differentials were differentials for functions of one variable. In Calc 3, and as we're going to use them, the differentials are total differentials for functions of two variables. All right, and the basic definition for what a total differential is, a total amount of change, if we have a function of two variables, you can have a small change in the x variable and a small change in the y variable, contributing to a total change in the function value. And it's basically what the partial derivatives represent, a amount of change with respect to one variable. All right, so we're going to introduce the notation in a little bit, but this might look familiar if you've gone through Calc 3. It's basically differential notation for partial derivatives. All right, so let's kind of explore the the background knowledge that we're going to use from Calc 2 differentials and how we're going to take it to multivariable differentials. So let's just focus on the Calc 2 side of the kind of differentials. If we choose our u, we calculate du by differentiating. All right, we should be able to go backwards. How do you undo a derivative? Kind of the main theme for our course. You would integrate. All right, so let's relate that now to the multivariable differential idea. Let's suppose we have our u as now a function of x and y. Well, we can still calculate du, what we're calling a total differential, but now that requires partial derivatives. For differential equations, we have to understand how we go backwards. And again, as always, we undo a derivative by integrating. So conceptually, it seems rather simple. What we have to get to is how partial derivatives work and how do we integrate and go backwards with functions of two variables. All right, so let's go back to our intro example, which I have on the bottom of the screen here. So it's the kind of alternate version that we rewrote it as in differential form. Right, and notice right below, I'm putting what we're calling now a total differential. They look very similar, right? They have dx in both and dy in both. All right, now if you look at the Calc 3 part there about differentiating and integrating, going backwards there, well, that looks very similar to our intro ODE. What we want to be able to do is go backwards, undo the derivatives by integrating. So notice there, if we go backwards from the total differential, by integrating, we should get the function f of x comma y. And that is going to be what we call and view as the solution to our ODE in differential form. Now the solution by itself is not the function of x and y, but it's the function of x and y equals some constant. And that constant's there because what differentiates to 0? A constant. This will all make some more sense once we get to what partial derivatives are and start looking at an example of a total differential to relate it to one of our ODEs. All right, so for the next part, we're going to go through a quick crash course in partial derivatives, saving a complete description of them for multivariable calculus. We'll just go through them at a level for calculations as we'll use them. All right, so the main change for partial derivatives is it's a notion of derivatives for functions of two variables. So instead of having a single independent variable, we have two independent variables, x and y. All right, and with that, it kind of opens up having to move the ideas of calculus into 3 dimensions. X and y are your independent variables, and you would need a third variable or axis for the function value. And typically we choose that as z. So transitioning to multivariable functions, we have to move into the x, y, z 3-dimensional coordinate system. Don't worry, we're not going to do that. We just need to keep in mind that we now have 2 independent variables, x and y. All right, for this function of 2 variables, you can calculate a partial derivative with respect to x, and you can separately calculate the partial derivative of that function with respect to y. All right, and the notation there is very similar to differential notation, dy over dx, but it's kind of changed to cursive or squiggly differentials to emphasize that the function now depends on 2 or more variables rather than 1 variable. All right, now a very basic idea of how partial derivatives work is we're going to treat one variable as the variable, the other one will be thought of as being constant. All right, now it tends to be kind of a little confusing to keep track of what's the variable and what's the constant, but if we're calculating a partial derivative with respect to x, the other variable, y, is thought of as being a constant. Similarly, if we're calculating a partial derivative with respect to y, the other variable, x, is now thought of as being a constant. All your familiar rules for calculating derivatives apply, just with this small change. One variable is the variable, the other one is a constant. Product, quotient, and chain rules still apply as usual, just with this one modification. All right, so we're going to slowly introduce the ideas we need to calculate partial derivatives. Let's think back to Calc 1 with 2 basic derivative rules. The first one, the derivative of a constant. And we all know that the derivative of any constant is 0. The other rule, which we can call the constant multiple rule, is when we have a constant multiplying a function of x. And what this rule allows us to do is basically bring the constant in front of the derivative and just have that constant multiply the derivative of the function of x. You've used these rules and you probably even haven't realized it going through Calc 1 and through Calc 2 to get to our course. All right, now the change here comes with calculating partial derivatives with respect to one variable of a combination of x and y. All right, so without introducing any examples, in this Calc 3 example, let's suppose for the first one, we calculate a partial derivative with respect to x of the function x. Well, that should be exactly what you're used to. The derivative of x with respect to x should be 1. And that's still the case here with a partial derivative. Now, the big change is if we calculate a partial derivative with respect to x, but of now y. When you calculate a partial derivative with respect to x, y is a constant. And just think for a moment, what is the derivative of a constant? 0. We just have to remember and keep track that when calculating a partial derivative with respect to x, the other variable y is a constant. So that's why the partial derivative here of y evaluates to 0, because we're thinking of y as a constant. All right, similarly, to kind of mix up the variables, if we calculate, this is the right side, if we calculate a partial derivative with respect to y of the function x, now x is thought of as being a constant, and the derivative of a constant would be 0. At the bottom there, the partial derivative with respect to y of y should be 1. Provided the variables match in the upper left example and the lower right example, it seems to be your familiar rules, just with different variables. So just be sure to keep track of what variable is the variable and which one is thought of as being a constant. When you're ready, we'll get to some basic examples just to calculate progressively more complicated examples on partial derivatives. All right, so this is a good point to kind of tailor this to 2 different groups of students. So for those of you that have completed multivariable calculus, pause the video, give yourself a chance to complete parts A through D. If you have a solid understanding of Calc 3 and partial derivatives, these should be no problem for you. The other group of students, those of you that have not completed multivariable calculus yet, we're going to go through part A together and then slowly give you a chance to try parts B, C, and D, which gradually get more complicated. All right, so if you're ready, let's get to part A. All right, so our function here is 2x cubed y squared. And when asked to calculate the partial derivatives, plural, there's 2 of them. A partial derivative with respect to x and a partial derivative with respect to y. Now, what I want to do for our first example in going through this together with you is try to make this look like some of those Calc 1 rules so we get a good understanding of how we use them to speed up calculations later. All right, so let's calculate the x partial derivative of this function first. Make sure you recall and realize when calculating an x partial derivative, y is a constant. Now, back to Calc 1, what can you do with constant multiples? You can pull them out in front of the derivative. That works for ordinary derivatives, and it also works now for partial derivatives. Just keep track of what are the constants or constant multiples. Here, it's 2y squared. So I can pull 2y squared in front of the partial derivative, and now just partially differentiate x cubed. And that works as you would like it to. The partial derivative of x cubed with respect to x is 3x squared. Basic power rule. All right, and now 3x squared, we just multiply that to the constant multiple 2y squared. So we get as our simplified answer for our x partial derivative, 6x squared y squared. All right, let's do the same thing for now the y partial derivative. The change for a y partial derivative is now that x is thought of as being a constant. If this seems to be making sense, again, for those of you that have gone are being introduced to partial derivatives for the first time here, maybe pause and give an attempt at this. If not, just continue and we'll immediately go through this. All right, very similar to above, we're going to pull out the constant multiples. Now our constant multiples are 2 and x cubed. So we can pull them out and now partially differentiate y squared with respect to y. And that also works as you would like it to. The variables match. You're differentiating y squared with respect to y. That should come out to 2y. And 2y, that now multiplies the constant multiple, 2x cubed. So we get as our simplified y partial derivative, 4x cubed times y. All right, this is about as simple as it gets for an example on partial derivatives. If you're ready, let's combine all those ideas in part A here to a slightly more complicated part B, since there's now multiple terms, unlike the single term we have in part A. All right, when you're ready, let's get to part B. All right, again, if you feel confident, pause the video and maybe make an attempt. If not, we'll go through it. We'll check in a few seconds in case those of you want to continue immediately with going through this. All right, now, as we go through this, there's a lot of other differentiation rules which we could state, but you use them so often, you probably don't even realize it. We're going to use some of them here. Notice we're adding and subtracting a lot of terms here. And we have a rule, the sum and difference rule, which allows us to differentiate each term and then add or subtract them all together. We're still going to use that idea here, but now with partial derivatives. All right, so let's calculate first the x partial derivative of this function. We're going to differentiate term by term. We don't need the product rule for this example yet. Even though we're multiplying, notice x cubed y, that is a product, but it's not a product of functions of the same variable. We have x cubed times y. We can view this for each individual partial derivative as the constant multiple rule, if we remember which variable is thought of as being a constant. So if we start by differentiating with respect to x, that first term, x cubed y is thought of as being a constant right now, and we can just differentiate x cubed to get 3x squared times y. When we move to the next term, negative 2xy squared, again, we're thinking of y as a constant, so differentiate x, and you would get 1. The negative 2y squared, that's just your constant multiple. And differentiating with respect to x, 3x squared, that still works out to what you would expect, 6x. Now, the only change here with calculating this x partial derivative is to be careful with differentiating 2y. We're thinking right now of y as being a constant. And what is the derivative of a constant? 0. So the last two terms, 2y and 1, both partially differentiate to 0. All right, let's go through the y partial derivative, which is very similar. Now the change, a partial derivative with respect to y, we think of x as being a constant. And if we differentiate term by term, x cubed y, we differentiate y, which would become 1 for its partial derivative with respect to y, and 1 would multiply the constant multiple x cubed. All right, we can move to the next term, negative 2xy squared, and partially differentiate that with respect to y. Negative 2x will be thought of as a constant multiple, and we differentiate y squared to get 2y. All right, 3x squared, since x is a constant, is entirely a constant. So 3x squared will partially differentiate with respect to y to 0. The last term that remains in our partial derivative here comes from partially differentiating 2y. That would differentiate to 2. All right, so part B was a little more complicated, incorporating now several terms, but the product rule was not needed since we can think of these terms as being constant multiples of the other variable. All right, let's move on to part C. This is an example where we're going to need the product and chain rules. So again, if you're interested, pause to give an attempt at this. If not, we'll check in a few seconds. All right, welcome back. So let's go through both partial derivatives. What I want to do is start by going through the chain rule for where we're going to use it for part C. All right, the chain rule is going to come in when we now try to differentiate that function e raised to the 2xy. Recall the chain rule is our rule for differentiating functions inside functions. All right, so let's do first the x partial derivative of that exponential function. So the outer function is e, or the exponential function. Recall that differentiates to itself. And what we need to do is, from the chain rule, multiply by the derivative of the inner function. The inner function right now, or inside, is 2xy. The only change for now partial derivatives is we multiply by the partial derivative of the inside. All right, and since we're doing an x partial derivative, we're going to calculate the x partial derivative of that inside. So differentiate with respect to x, 2xy. That'll come out to 2y. So that's how we use the chain rule here, now incorporating partial derivatives. All right, before moving on, let's also calculate the y partial derivative of this exponential function. It's very similar. The only change is now the y partial derivative of the inside, or inner function. That would come out to 2x. All right, so if we start to incorporate that into answering the question, let's do the easier partial derivative first for part C here. All right, and that is the y partial derivative. The reason for that, notice in the definition of the function, we have x squared times the exponential function, which contains x. So the function that we're given is a product of x squared times another function of x. So we're going to need the product rule to calculate the x partial derivative. For this example, the y partial derivative, we can just think of x squared as a constant multiple. So if we bring x squared out in front of the y partial derivative, we basically already worked out above the y partial derivative of that exponential function. The x squared factor that we pulled out just stays as a constant multiple. All right, so for this part, the y partial derivative, we only need the chain rule. All right, let's go through incorporating the product rule for the x partial derivative. All right, and we're going to think of this as x squared times the exponential function. Now the product rule we apply it by differentiating the first function, keeping the second the same, and then adding to that the first function times the derivative of the second function. Only change now for multivariable functions is we replace derivatives with partial derivatives. All right, so if we partially differentiate the first function with respect to x, that works out to 2x. We multiply by the exponential function. We then add to that x squared times the x partial derivative of the exponential function, which we worked out above with the chain rule. All right, if we put it all together, that's how we incorporate the product and chain rules into partial derivatives. All right, if you feel okay, let's move on to the last example, which is the most complicated one of all, part D. All right, if you're up for the challenge, if you're new to partial derivatives, pause to make an attempt at this. If not, we'll just pick back up in a few seconds. Welcome back. Hopefully this one isn't too intimidating. Let's go through it. We just have to be careful with how we kind of view this to start. Notice that first term, x squared y times sine of xy. We have a function of x and y out front of the sine function, and then sine within it contains x and y. So we're going to have to use the product and chain rules for each of the x and y partial derivatives. That's why this one's a little more complicated than part C. Part C only required the product rule being used once. For part D here, we're going to need the product rule for both partial derivatives. All right, so let's just conceptually work out the product rule first. So we'll start with the partial derivative with respect to x. So we're going to differentiate the first function or factor, x squared y, with respect to x. We then multiply by the second function, sine of xy. And then we add to that the first function, x squared y, but now times the x partial derivative of sine of xy. All right. In the function, there's that very last term, cosine of y squared. Keep in mind, for an x partial derivative, how do we interpret y? We think of y as being a constant. So the last term in the function, cosine of y squared, that partially differentiates to 0. Okay, before we advance, this is where we get with the product rule. Let's now calculate those remaining partial derivatives there. So the first part, the partial derivative of x squared y, that'll work out to 2xy. And if we again apply the chain rule, we partially differentiate the outer function first, sine, that differentiates to cosine. We keep the inside the same, xy, but now we multiply by the x partial derivative of the inside. And the x partial derivative of xy would be just y. All right, the y partial derivative for this function is very similar. When you're ready, we'll go through that. And again, we'll start by applying the product rule. All right, so the product rule applies to the first term in the function, x squared y times sine of xy, very similar to what we did for the x partial derivative. But now, since we're differentiating with respect to y, we can differentiate cosine y squared to get a non-zero result. All right, and that's included at the very end there. We're going to apply the chain rule for that. So for the last term, cosine of y squared, we differentiate the outer function cosine. That turns to negative sine. Keep the inside the same, y squared, and then multiply by the y partial derivative of the inside. Y squared would partially differentiate to 2y. All right, the first two terms come from the product rule there. So very similar above. We're going to differentiate x squared y with respect to y, multiply by sine of xy, and then we add to that x squared y times the y partial derivative of sine of xy. All right, the calculations are extremely similar to above. And if you work them out, the partial derivative of x squared y should come out to now x squared for that y partial derivative. And then the partial derivative of sine of xy would come out to cosine of xy times x. All right, this one we can simplify and clean up a little bit and get this final answer for our y partial derivative. All right, now either that was a review or an introduction to partial derivatives. Even for those of you that have completed multivariable calculus, this was probably a good review anyways. All right, I want to close this first part to kind of bring this all together. So how do we relate partial derivatives, total differentials, to ordinary differential equations? Let's create a differential equation by using example 1a that we just went through. Now, in the example a few minutes ago for part A, we were given the function 2x cubed y squared, and we were asked to calculate the x and y partial derivatives, which we have here. Pretty simple, very straightforward. All right, what I want to do is with these partial derivatives, we can define the total differential for this function. We take the x partial derivative, multiply it by dx, and then take the y partial derivative and multiply it by dy. Okay, so great, we just set up and calculated a total differential, basically a combination of your x and y partial derivatives. All right, we're going to turn this into an ODE. Bear with me. All right, conceptually, we should have this relationship. We can go from the function to the total differential by differentiating, and we should be able to reverse that, going from the total differential backwards to the function by integrating. All right, what I want to do is take that total differential, and I'm going to set it equal to 0. Why? It looks very similar to what we're calling an ODE in differential form. Now, we actually have, for this ODE in differential form, the solution on the screen. View that ODE as being the total differential of some function. How do you undo a derivative? How do you undo a total differential? Integrate. So if we go backwards, we should get to our solution for the ODE, which is that function that we started with to calculate the total differential, 2x cubed y squared. Now I realize this might seem confusing, But if you're keeping track and following along, if we have that ODE in differential form, the solution is the original function that we started with to get those partial derivatives. 2x cubed y squared. And then in order to get the 0 on the right-hand side, what differentiates to 0? A constant. So that's how we turn partial derivatives and a total differential into an ODE. What we have to address is how we go backwards. How do we perform this integration? Now, in the next part of this lecture, we're going to introduce ways to answer these two fundamental questions. When is an ODE the total differential of some function of two variables? And then when it is the total differential of some function of two variables, how do we find that function? Because that function, what we've been calling here, f of x comma y, that is basically the solution, provided we set it equal to a constant. So that function, which we're going to learn how to find, that is basically the solution to our ODE in differential form. All right, this is it for part one, kind of introducing what ODEs in differential form are, reviewing partial derivatives or introducing partial derivatives for the first time, and then relating total differentials to what we're going to be solving, differential equations. Part two will continue with this.